Hello, and welcome. Welcome to our Yebo Tutor session on chemistry. My name is Nyasha. I'm going to be helping you out here and there with your chemistry grade 11. And later on into the year, we'll skip to grade 12 and start working out some problems that are based on your question papers. So, how is the new year? How is the new year? Are we starting off well in the new year? I hope we are starting off well. So what's happening is that I'm seeing a message right now. From one of your organizers. Let me just see what they're saying here. Please give me a moment. Just see what's happening here. Right, just give me a moment. I need to hear what's happening from your organizers. Okay, I think we're good now. We're good to go. Right, so welcome back to chemistry. So what we want to do is to, this year, since we are starting year on a fresh note, we want to pick the sectional arrangement of topics, right? The sectional arrangement of topics in such a way that we will obviously work from past papers, right? We'll obviously work from past papers. But the idea is we want to take a specific topic and pick the selected questions, let's say from 2015 upwards, that are under the topic in each paper. Okay, so just a quick rundown of your topics. I'm sure you know this already. I'll just do it for the sake of those that may have forgotten. Right, so your syllabus is obviously guided by the National Curriculum Statement. And what I will select is one of the pages that shows the general layout of your syllabus. So let's just see if we can get to that. It has the general topics. There we go. So this is what we want to outline and see what we can focus on. So for grade 10s, obviously you do physics, right? So when you start your grade 10, if you're starting a grade 10 this year, congratulations, welcome to high school. So that's your grade 10 physics topics that are listed there. Grade 11 topics that are listed there, and then grade 12. So here, what we are seeing here are the various main topics in bold and the subtopics as listed. Obviously, we are different in our approach. We've got someone specifically for physics. So I will be focusing on your chemistry. When you look at your chemistry, you're starting from, let's say, after this electricity and magnetism. When we start talking about matter and materials, that's when your chemistry pops in. So as far as your topics are concerned, you've got a section on revision, right? So this is probably taking from what you were studying earlier. Right, so this is taken from the revision. You've got revised meta and classification, that's materials, heterogeneous and homogeneous mixtures. Let me just scroll out of that. Let's see if you can see, oops, sorry, I meant out, right. So I need just 230 here. Okay, I think that's good enough. So what we want to just see are these subtopics. So then after you've done mixtures, pure substances, names and formulas, metals and non-metals, electrical, thermal, conductors, and insulators. Right? So all these are basics of materials. And when you look at the classification of our materials, I think immediately you should have your periodic table. So let me just see what the periodic table shows here. So the periodic table that I'm pulling is from one of your papers, right? So it's from the grade 11 paper 2 on physical sciences. So usually you'll be provided with a data sheet. So this is a set of documents that have printouts of constants. So for example, you've got this table, table 1, it is just physical constants, right? And these are numbers that do not change. And these numbers will change after a very long time, but no, in general, they are agreed upon. So we've got Avogadro number 6.02 10 to the 23 per mole. It has to do with the amount of substance, right? It can be substance in the sense that it can be atoms, it can be molecules, as long as we're talking of the number of particles. That's Avogadro's number. Then you've got the molecular gas constant. Depends on the topic. You might use it, you might not be using it. Standard pressure, that's our atmospheric pressure. And we've got VM, which is the molecular gas volume at standard temperature and pressure. And you've got your standard temperature, which is 273 Kelvin. Okay, then the second table is just formulae, right? Formulae table, these are common equations that you use. You obviously are working through lots and lots of equations, right? So these are different equations that you use. You might be using them now, you might be using them later, so just get used to how it's laid out, get used to how the equations are used. Also calculate using these equations. The topics, it depends when you're studying it. So in case you are entering a revision stage, let's say you're in grade 12 right now, obviously you would need to remember some of these basic topics. So you've got your equation for your moles. You also have your equation in terms of the number of particles, right? In terms of the number of particles. Then you also have in terms of volume, and then you've got your concentration equation. Right, then we can now see the periodic table. Let me just tilt it, right? Let me just rotate it so that we can see how it looks like. The periodic table, let's just see who's around Yebo. Let's just see who's around Yebo in case you are joining us for this discussion. If you're joining us for this discussion, just let me know how you do it at your school, right? At school, where you're studying. How do you do it in terms of the arrangement of your periodic table elements? So I suppose that your teacher could have given you the standard periodic table where you've got some table that has elements and their properties. So just in general, you've got an example. So these are all the elements, right, that are known up to now, right? These are all the elements that are known up to now. So what we have is an arrangement of the elements, and they are arranged in a certain pattern, and there are certain trends that these elements are arranged according to. So what we can pick is defined in this key. This key will tell us that this element has this symbol, right? The element has that symbol. So if you read in your notes now, if you read in your even in Siavula textbooks that you can find for free online, which are very, very well explained textbooks, you will find that there are some names that are associated to certain symbols, right? So you've done this in class, I'm sure, several times. You've got this symbol for copper. Then you will be given the properties. One of the properties is the atomic number. The symbol, we've already identified it. The approximate relative atomic mass is given there, and its electronegativity. Those are given there. So each element, so if we would come to any section of this table and look at copper, this is what we were shown as an example. So copper has that symbol, and then it has that atomic number, electronegativity of 1.9, relative atomic mass of 63.5 grams per mole. Right. Then you've got other elements like this element which I like, titanium. So it's got its atomic number. You also have its electronegativity, and you've got its relative atomic mass. Right. So that's your periodic table. So it's one of the other tables that you would benefit by making use of all the time. Just get a print out that you can keep reading and using, referring to in class. Then we will scroll down to see, let's say, trends. Okay, so when I was talking about trends, when you study certain topics, for example, you're looking at electronegativity, you will notice that your electronegativity increases, isn't it? So that electronegativity, it increases as you approach elements that are positioned on the rightmost part of the periodic table. Okay? So you've got your electronegativity, 1 for lithium, 1.5 for beryllium. Then you've got 2 for boron, 2.5 for carbon, 3 for nitrogen, 3.5 for oxygen, 4 for fluorine, and so forth. So those are your electronegativities. And these obviously have to do with reactions, right? They have to do with reactions. Okay, then we've got some more tables here. This is now some electrochemistry. So these are standard reduction potentials. These are some standard reduction potentials. Table 4A, reduction, and then table 4B, you've got also standard reduction potentials, and you're continuing with the set of elements. So they will give you the reduction potentials. Depends if you've done this topic. If you've not, then you don't need to worry yourself. But otherwise, those are the things. Number 1, we've got some constants. Number 2, you've got some equations. Number 3, you've got your periodic table. You've got your reduction potentials at the end. So which means if you can just print these out and use them every other time, I think you can benefit by doing that. So we said we want to look at the topics that have to do with, let's say, atomic structure. Then we'll look at molecular structure. The atomic structure is obviously the precursor to molecular structure as a topic. So I was just highlighting the periodic table and the table of constants from the idea that had been raised by this part of the syllabus, metals and non-metals. So we also have states of matter and the kinetic molecular theory, right? You also have the periodic table, that is what we have just seen. And from the periodic table, we're interested in what? In the position of the elements, right? Position of elements, similarities in chemical properties, electron configuration. That one is also physical chemistry. Then bonding, right? Bonding, chemical bonding. So you've got bonding in between elements, right? That is chemical bonding. You also have some bonds in between molecules. So you will notice that bonding is separated into what your covalent, ionic bonding, metallic bonding. These are all defined. I suppose you've done those, right? And then particle substances. These are different particles. Atoms, compounds, molecular, different substances made up of those particles. Molecular structure now. Molecular structure now is our grade 11 starting point. Molecular structure is our grade 11 starting point for chemistry. So because we are focusing on grade 11 and grade 12, we will look at this molecular structure. But whichever way, we can just go through the syllabus so that we can see what are the topics and what are we expected to cover this year, grade 11 and 12. Okay, so molecular structure deals with a chemical bond. Right? Remember, there's chemical bonding already introduced in grade 10. So molecular structure deals with a chemical bond, molecular shape, electronegativity, and bond polarity. Electronegativity and bond polarity. So if you are looking at molecular shape, right? If you are looking at molecular shape, first of all, you've got an atom that you build. So for example, we can just use one of the gizmos here to build an atom, right, to get the properties of an atom. So let's just build an atom and see what element it represents. Right? Let's build an atom, see what element it represents. For us to come up with some reasonable order of doing things, we can maybe look at the periodic table, but we'll blindly look at it. So what we want to do is we do not want to look at the element. Right? We do not want to look at the element. We want to just look at its properties. Let me rotate it once again. There we go. So I want to look at its properties and just collect that information of its properties. So for example, oxygen. So I'll just delete this for now, right? All we want is to put in some of the properties that have to do with its atomic number, its number of protons, and its number of neutrons. So this is our element. So let's jump onto our tool. So this tool is courtesy of a university called the University of Colorado. They've made a very nice instrument that you can use here. You can even find it for free. You just go online, then you just type PHET simulations. So there's a lot of material. Some of it is university level, but there's also there are also a lot of basic tools so that you can appreciate how we come up with these atoms, elements, and also some topics. There are several topics that are discussed. Got some tools to play around with there. Right, so we want to just build an atom. Why are we building an atom? We need to focus on how we end up putting atoms together to then form some molecule which has some molecular shape, right? So then we can look at a question that has to deal with that. So let's build the atom. when we are looking at this atom, it has this atomic number. What does atomic number represent? What does atomic number represent? So this is our atom that we have been given in this question. We do not know which element it is. We do not know which element it is. But for this unknown, element, its atomic number is equal to 8. So this atomic number is equal to 8, and its relative molecular mass is equal to, the relative molecular mass is obviously the number that is below there, right? So this is the relative molecular mass. So that is 16. So we now want to just find out the number of protons. The number of neutrons, so that we can find its identity. Right. Number of protons, number of neutrons, then we can find its identity. So if we have been given this information that this particular element has an atomic number of 8, what is the number of protons of this element? What is the number of neutrons if we know its relative atomic mass? Right? If there's someone who is following, you can just drop in your question or your comment. Okay, so we can derive its number of protons from its atomic number, right? We can derive its number of protons from its atomic number. It's an identifying number. So we can take our number of protons and we can write that, okay, this element has 8 protons. So let's just build it. Let's build it. So what we have in this interesting display, is a method of building the element. So there's some protons here, there's some neutrons there, there's some electrons there, right? It has some protons, it has some neutrons, it has some electrons. Right, so for every proton that I put into the element, I will also put an electron into the shell. Why? Because I do not want to build a nucleus. I want to build an atom. I do not want to build an ion, so I will put an equal number of protons and electrons. Right, so let's put the 8 protons. There we go. 1, right? 2. There are some names that are already being suggested. I guess you can see that. We just want to get to our 8 protons, right? There we go. 3, there we go. 4, there we go. 5, 6, 7, 8. So we now have 8 protons. Let's put in some electrons. 1, 2. We fill in the what? The innermost shell first. Then we go 3, 4, 5, 6, 7, 8. So we now have a neutral set. Now, how do we find the number of neutrons? How can we find the number of neutrons? How can we find the number of neutrons? Our neutron number must be equal to what? It's equal to the relative atomic mass. So let me put this as, because this is a single atom. The relative atomic mass, which is our 16, minus this given proton number, which is 8, so that we can get an 8. So let's throw in the neutrons. The first neutron is in, the second one is there, the third one is there, 4, 5, 6, 7, 8. Now we have our correct number of neutrons. We have an equal number of protons and electrons. Our atom is balanced, or it is showing it's stable, right? If we did not have enough of the electrons, we can already see an indication that this is now an ion. But if we put in all the electrons, then we have a neutral atom. Okay, so in that case, which atom is it? The indication is oxygen. So we now know that this atom is an oxygen atom. Whenever we are now using the oxygen atom, this is the basic structure that we always need to remember. So there's some information on charge, mass number. If you like to use that, if you're studying at that level, you can then use parameters. So now from this exercise, we can agree with the program that indeed this was what? This was oxygen. Right, so that's where you would apply your basics of the of the atomic structure. So you get your atomic structure from there. That atomic structure is what you use for you to consider chemical bonding, isn't it? Because we share some electrons in covalent bonding. There is some electrostatic charge that leads to attraction in the form of ionic bonding, and then we also have metallic bonding. So after the chemical bond and the molecular shape have been understood from the basics of how the structure of the atoms are laid out, then you will need to remember your electronegativity and bond polarity theory. So all these are useful for you to build understanding of the molecular structure and the forces that can act in between the elements and also the molecules. Intermolecular forces, you have, you revise your chemical bonds. So you've got some types of intermolecular forces, the states of matter as a solid, liquid, and gas. Then you've got density, and kinetic energy, temperature. These are what? Properties, isn't it? These are properties now. Density, kinetic energy, temperature, right? And the three phases of water. The three phases of water. So just a quick revision of how it may look like. There is a nice tool here that can tell us about the phases or the state in which matter can reside. So what we have in that small, should we call it an image? What we have in that image is a setup of something that we can call a calorimeter, or just something that is closed, right? So there's a hand here, as you can see. This hand is what is closing this lid. So all the particles that are in there are locked up. So there is no interaction with the external environment. Okay. So what does it mean when we have a material in its solid, or in its liquid, or in its gaseous state? What does it mean? So when it is, so we can say the state of the material, and then we can state the arrangement of atoms. So atoms, or we can even write it as atom mobility, atom or molecule mobility, molecule mobility. This simply has to do with how fast the molecules are moving, how fast the molecules or the atoms are moving. There are some elements such as noble gases. They exist in the gaseous state, right? So you can find neon, xenon. These are just noble gases right here. Helium, neon, argon, plankton, xenon, and so on. So these can actually exist in the gaseous state, right? So we just need to see how they move. How do they move? So we will first obviously look at the solid, then we will look at the liquid, and we will look at the gas state. The solid, the liquid, and the gas. Right, so right now, I would like to select an element that we know and we are used to. For example, right? So this is an example of water. And what we have here are some gauges that show the temperature at which the water exists. The temperature at which the water exists. Remember the kelvins that we pointed to. There's some kelvins that we pointed to. So I think we were here. Were we? No, it was on the constants. So on the constants table, let's normalize it. Yes. So for example, we measure standard temperature in what? In Kelvin. We also have some calculations using temperature in Kelvin, isn't it? We also have some calculations using temperature in Kelvin. So these are some of the numbers that you need to get used to. So what I just want us to do is to look at this arrangement that we have in here so that we understand the numbers. So the numbers that are displayed there, we've got a 146K that is displayed there. That is the temperature. This is the temperature gauge, so it's an indication of a thermometer, right? So this thermometer measures the temperature of water. Right now, the temperature is at 146 Kelvin, right? It is at 146 Kelvin. So when water is at 146 Kelvin, is it in the solid, the liquid, or the gas state? Is it in the solid, the liquid, or the gas state? So there we go, 146 Kelvin. T is equal to 146 Kelvin. What is this equal to? So I'll call it T in Kelvin. What does this correspond to in degrees Celsius? What does this correspond to in degrees Celsius? Would you like to make that calculation? Would you like to make that calculation? What does it correspond to in degrees Celsius? As far as your temperatures are concerned, you know that, for example, the freezing or the boiling point of water have certain known values. So I think we also saw one of the values in here. It's the table of constants, right? Okay, standard temperature, there we have it. Right, so this is our standard temperature. So our standard temperature corresponds to what? How many degrees does this standard temperature correspond to? How many degrees does this standard temperature correspond to? How many degrees does it correspond to? When you find this standard temperature corresponding to 273 Kelvin, this is equivalent to a temperature in how many degrees? T in degrees Celsius of the standard temperature. Let me put it here so that we can put the Kelvin here. And I can put this. So this is just a symbol to indicate that I'm now discussing the same standard temperature, but this time in degrees Celsius. So I am asking how many degrees Celsius does a standard temperature of 273 K correspond to? When you find that temperature, then you can decide if 146 K or Kelvin is greater or less than the boiling point of water or the freezing point of water. So we want it in degrees Celsius. When you've done that, then this gadget should make sense on the state in which our water is. What is the state of this water? When you heat the water and raise the temperature, when you hit the water and raise the temperature, there's something that we should be able to see. Right now, maybe let me lower the temperature again, try to get to 0 Kelvin, right? Try to get to 0 Kelvin so that we can see what happens with the molecule. So I'm now lowering the temperature, which is a process of putting an ice, putting some ice there that is representing an object that is at a very low temperature, right? And it is all the energy that was stored in the molecules of water is being transferred to this coolant. So look at our molecules now. The molecules are bound together tightly and they're not mobile. So this is very close to reminiscent of the solid state for water. Very low mobility. Very low mobility of the particles. Very low mobility. It's in the solid state right now. It's not moving. Let's get something else of the options that are available here and also drop its temperature. So I'll just restart this and we are selected on neon, right? We're selected on neon. And then I'll drop the temperature again. Can you see what's happening to the neon atoms? There's something that's happening there, right? So let's drop the neon atoms. Let's drop the atoms. Let's drop the temperature of the atoms. If you were to compare with what you saw earlier, what can you say as far as neon is concerned? Neon atoms are now less mobile again. They're now less mobile again. So mobility is what? Is very low when we are at when we are in the solid state. I'm simply freezing these, so it's a gas, isn't it? If I freeze it, it becomes a what? If I lower the temperature, it changes to the liquid state, then it goes all the way down to the solid state. So mobility of the atoms is very low. Let's go and see argon. Argon is argon. We've got some temperature of 43 K this time, and we'll drop the temperature again. So if we cool the system and we drop the temperature, the argon is now approaching 1 Kelvin, right? It's the best that this system can give us as an example or as a simulation. So now we can see that the argon atoms as well, they are what? They're stuck. They're bound, tightly bound, and they are less mobile. Bound and less mobile. Oxygen is I think it's a similar case. If we drop it, if we drop the temperature all the way down, they become less and less mobile. The same applies to the water that we saw earlier. So there are different materials. We can forget about some of these other diagrams. They're not necessary right now. So what happens now in the liquid state? What happens now in the liquid state? Let's take water, right? Let's take water and make it a liquid, right? So at what temperature do we have water in the liquid state? As long as it's above the what? The freezing point. So even if we take it to 5 degrees Celsius, we take it to 10 degrees Celsius, we take it to 90 degrees Celsius, it will be in the liquid state. So you do the conversion again, right? This was a method of converting. We were trying to find out the temperature in degrees Celsius. So you do the calculation here. It's a very straightforward conversion equation. So what I want us to do now is to take all these substances into the liquid state, right? Into the liquid state for water, what we are seeing is that we've got some, let me go to 273 standard temperature, 273 standard temperature, right? So I'll just go slightly above standard temperature, right? So for water, do you see what's happening now? For water, we are slightly above the boiling, the freezing point. So we are now seeing water molecules. And as you can see, the water molecules are still bound together. The water molecules are not completely dissociating, right? They're still bound together, but they are more mobile, right? So we can say moderate mobility. This is moderate mobility. The molecules are moving around, isn't it? They're moving around. The same must apply obviously to neon. If we are at, let's just boil it. Right. So what I want to do is to avoid to get to the boiling point, isn't it? So you need to know this material and its properties. That's where this topic comes in. Where is it? We identified it somewhere. This is where this comes in. So this is where you learn about your properties of different materials. So for the temperature that I was at, right, this was the freezing point. I'm just dropping the temperature again. Just dropping the temperature again. There we go. So it's now at 1K. So it is now not mobile at all. You can see the atoms are just bound together. The mobility is very low. So if we raise the temperature a little bit, we can see some activity, right? We can see some activity. Right, let me just take this. I need to freeze that particle as well. Look at its velocity. Dropping, right? So now I'll just raise the temperature for all the particles. 3K, raise the temperature a bit. 4K, raise it to 10K. As you can see, look at the mobility. We are not worried about the details right now. We need to understand what's happening in the first place, isn't it? We need to understand what's happening in the first place, what is taking place, so that when we write down the equations of the chemistry and all that, we are well aware of what exactly is taking place. And as you can see, at 20K, neon has some mobility, right? Neon has some mobility. Let's see argon. The same should take place. When we started, we had frozen it. We'd taken the temperature to absolute 0. So it's now at 1, okay, almost absolute 0, right? So it was at 1K. Then we can start raising this temperature. So as you can see, when we raise the temperature, these argon atoms are becoming more active, right? As you increase the temperature, these argon atoms are becoming more mobile. So they are approaching a liquid state which has a moderate mobility. Just the same way a liquid that you put in a fluid, you can literally change the shape of the fluid, change the shape of the occupation of the container by moving around the container. Then the fluid will just follow, the liquid water will just follow the shape of the container, right? So I think if we could rotate and move this around, we could see that, but we can't. But you know it. I mean, even the water can do it at home. Okay, so oxygen, the same applies when it is frozen. Right? When it is frozen, there's very little atom mobility. Right? When it is frozen, there is very little atom mobility. It's oxygen, so it stays in pairs. So in our case, we will now say molecule mobility. Then when we add in some heat, we will get to a state where it collapses, isn't it? This is still a solid state. This solid state must begin to take the shape of the container. So this solid state must actually disintegrate, right? It must take the shape of the container. Right now, it's still semi-solid because it's not yet filling in the shape. It should settle, isn't it? If it's a liquid, so it's not yet at the liquid state. We are heating it, right? The atoms, so the molecules are more mobile. Let's heat them. Look at what's happening. Look at that. What's happening? Look at what's happening. It's beginning to spread out, right? It's beginning to spread out. There we have it. So our oxygen is beginning to spread out into its liquid state. Right. Moderate what? Moderate motion of the particle. Let me just see if I can keep heating it. Yes, it's taking the shape of the container. Then obviously water, we know it. We are at 0. We said it's a solid, so it's obviously just particles. We can even take it to its original state, water. Yes, it was like that. So we're saying right now it's still a solid. It can be picked up. You can pick it up, right? It's at absolute 0. Then if you start heating it, We know that at 273, it should start taking the shape of the container, isn't it? At 273, it should leave its solid state, begin to change into the liquid state. Approaching 273, there we have the molecules. They begin to collapse and take the shape of the container. 275, yes, collapsing and taking the shape of the container. Right, so there we are. It's the liquid state now. The molecules are spreading out and are more mobile. Now let's take it to 100 degrees Celsius. Let's boil this water, right, and see what happens to the mobility. Boil this water, see what happens to the mobility. Remember, the moment you start carrying out calculations, at the back of your mind, it would be best when you have an understanding. You can at least picture what's taking place. So as far as physical chemistry is concerned, you can actually tell 373. 373. Right, we are now entering the what? The gas phase. So our water is about to boil. Our water is about to boil. Our water is about to boil. Right, so if it is about to boil, let me just raise it some more. Let me just raise it some more. Because you see, look at what's happening. This 373. So it's beginning to boil. And as you can see, this is a temperature at which it will actually coexist in its liquid and gas phase, because it's beginning to what? So the anticipation is that you should be able to see some particles of the steam. We know that water in its gas state is called steam. Okay, so let's just raise the temperature some more. So what's happening now? I've just raised it way beyond the boiling point. We obviously now see more and more of the particles. And that's what's happening there. More and more of the particles. That's what's happening there. And they're flying around. Right. So which means that we have an appreciation of these particles, and mobility is generally high mobility. Right, so if we were to do that to oxygen, which was initially down there at the freezing point, so let's draw it. I'll go way beyond the freezing point just so that all the atoms, this is oxygen, right? All the molecules have very little kinetic energy. There we are. So they've now dropped, they've now coagulated. Now that they've coagulated, we said the target is for us to take it to its boiling point. So I'll just keep raising the temperature, right? Look at those. We already have oxygen in its gaseous state. The gas state molecules, I keep heating. I'm now approaching, let's say, the temperatures at which we exist, 283, isn't it? Temperatures that we can relate to, 298 Kelvin, then we should be able to breathe this oxygen in because it's in its gas state, right? 273, that would be a 0, then 293 should be some 20 degrees Celsius. Oh, there we go. So now our oxygen is mobile. So that's why we're saying generally high mobility for the gas state. Okay, so much more can be discussed about this, but otherwise, we were just picking up aspects of these topics. Right, so intermolecular forces, we said they deal with all those properties, and then we can also look at ideal gases. So this is where you now talk about the kinetic theory, discussing about just now, which you said the particles are now increasing their mobility as the temperatures are raised. Gas laws, relationship between temperature and pressure. These gas laws, relationship between temperature and pressure, you will find the instructions, in fact, some of the equations here. So these are some of the equations that you can use when you're calculating the gas flows. So this year we hope to make sure that for each session we simply home into one of the topics that are here, right? So we circulate a topic, for example, ideal gases. Then we go into our different papers. So our papers, as you know, our papers are available online. So you can download a past exam paper for you to revise using. So we'll use one or two of per session, maybe per session we can have 5 papers so that we can have 5 questions that are in the same topic. Or we can have 4 questions or as many as we can. So just try to take them from 2015 coming upwards to 2020 if we can get such a paper. So our papers are obviously grade 11, grade 12 papers, depending on the topic that is being studied. Then the questions that we will take, you will notice that they are arranged like this. So we've got a topic there. Let's just pick a molecular or atomic structure topic. Why are we saying molecular structure? It is the first topic in our grade 11 chemistry. So you're already approaching grade 12 and you need to be prepared for this. By the time we finish, the objective is we would have done up to the last topic. So the paper will have a question here in multiple choice. So you've got multiple choice questions, and then you also have pre-response questions. So this is more guided though when you're writing. So you've got some section here which has some pre-response, even though it's guided as far as what is expected of you is concerned. So you also have, for example, the 2016 paper. So from what we just did, what I want us to finish off with is to just look at the rest of the topics, and then for the papers that I have here, the 2015 and 2016 as examples, what I want is for us to identify our topic, the first topic. Then we will just tick the questions that we will attempt together next week. Next week, so that when we are meeting, we are mostly maybe answering your questions. We are mostly looking at your questions. We are not really working things from scratch. Okay, so we'll finish up the topics now. So we said that will cover our grade 11 topics. Then optical phenomena and properties of materials. This is now the grade 12 level material. There is an experiment called the photoelectric effect, and then emission and absorption spectra. This all has to do with what we call optical phenomena. Optical phenomena, we are looking at light, or we're looking at waves, electromagnetic waves. But in our case, it's mostly light. So the photoelectric effect, you just shine some light onto some special material. That material is very sensitive to light. The moment light falls on it, there are some electric charges that it generates. So these electric charges, you can end up actually measuring them. Measure the current of the electric charges in a second. So the physics part, which is electricity, right? The physics part, which is electricity, electric circuits, right? Sorry. Okay. This is for grade 12. Let me rather go to this part. Yes. Electric circuits, which is still in grade 11. So that part, you will now make use of it in grade 12. When you look at the electric properties that are associated with the photoelectric effect, right? So please remind me, I think for the photoelectric effect experiment, the first thing is we have some photo for what? For light. And then electric. So these are some charges that are generated. There are some generated or liberated electric charges or charged particles. So there is an arrangement that is there that makes it possible for you to actually measure the current of those charges that are ejected, right? So the other word we can say ejected, right? They're ejected from the surface of the material. So there we have some of the applications of this optical phenomena, the photoelectric effect, emission and absorption spectra. So here we are talking about the graphs that you can draw to represent the intensity of some light at some wavelength, right? So there is an appreciation of the electromagnetic spectrum that is required here, because we are talking spectra, isn't it? In chemistry, you will do a lot of spectroscopy, maybe later on, maybe at university, but otherwise, you will look at a lot of properties of materials in terms of their absorption and emission spectrum. Right, then organic chemistry, functional groups. Right, so this is now a different section. We were looking at molecular structure. We are now at a different section, which is organic chemistry. So organic materials can be summarized in the form of functional groups. You've got saturated and unsaturated structures, you've got isomers, you've got naming and formulae. So there are many groups to consider in organic chemistry, and all you need to do is to mostly read. With the organic chemistry, it's mostly reading and techniques of identifying these groups. So when the molecule has been given to you, it may be a very long chain molecules. The structure, the naming of the molecules follows some structure. The naming of the molecules follows some structure. So it's important for you to try and revise those. Right. Then the next thing would be chemical reactions in organic chemistry, substitution, addition, and elimination, right? And we also have macromolecules such as plastics and polymers. So that would cover your work, which means for each subtopic, we will have questions that are related. So to end our short discussion for this year, for this beginning of this year, I will just ask you to identify the molecular structure questions that we have in our two papers. So this one, for example, I'm saying this paper is straight from the net, so you can download it. This paper is a grade 11. It's actually supplied on the main website of the Department of Education. Right? So you can find this on the main Department of Education website. Right, so this one is a 2015 paper, and then this one, I think, 2016, right? So what we have in these papers are the multiple choice questions, and then we just try to see if you can identify questions that have to do with molecular structure. Remember, what are the subtopics on molecular structure? These are the subtopics. We're looking at chemical bonds, shapes of the molecules, electronegativity, bond polarity, bond length, bond energy, intermolecular forces. So let's identify. So this one is on acids and bases. Is it part of a molecular structure? No, because we are just looking at properties of bases. This question, number of neutrons in an atom of nitrogen. So this one is just building an atom. We already did that question. Then, which one of the following is the strongest forces between its molecules? Intermolecular forces. They said strongest forces between its molecules. Strongest forces between its molecules. So you're already looking at intermolecular forces. So then criteria are what you then use to identify this. So we can actually say, just want to check where this question is disappeared to. Okay, so we can, this one you can check in one of the videos. We actually worked it out. Then which one of the following has a tetrahedral shape? Tetrahedral shape. What are we looking at here? Tetrahedral shape. We're looking at molecular shape. So when you have done the reading and you've done the lessons in class, then you can see how to apply this tetrahedral shape. So this is another question under molecular structure. Then let's see, 2 moles of hydrogen gas, standard temperature, pressure, occupy a volume of how much? Right, that's another topic. It has nothing to do with our molecular structure topic, right? Because we're looking at gases. It's fine. It's under ideal gases this time, right? So we won't look at it first because we're still looking at intermolecular structure. Then which one of the following correctly describes endothermic reaction? So this is now chemical reactions. Then 1.7, we've got some redox reactions. So these are now some electrochemistry basics. Then you've got another set of electrochemistry equations where we have oxidation and reduction. Then ideal gases, right? This is also ideal gases. Okay, so which means we picked 2 questions, right? Since we attempted these last time, we can start with them just to take off, but otherwise we can quickly identify the questions that we attempt here. So intermolecular forces. We have the type of bond formed between these is called a what? So obviously bonding falls under this topic because we are looking at chemical bonds. So obviously that question is part of our deal next week. The shape of the molecule, obviously, right? The shape of the molecule. Intermolecular forces, obviously, we'll attempt that. The bond energy, right? Bond energy. Do we have bond energy here? Yes. We look at bond characteristics and bond energy is one of them. So yes, we will have bond energy. So as you look at these questions, the notes that you are referring to are simply the so that we are comfortable with that topic, we move to another topic. Instead of you just taking the questions at random, you can do this at random when you're now at grade 12, you're revising and you're just having some fun. So this one is what gas, so that's ideal gases. As you can see these V's, we saw some equations, isn't it? Do you remember the equations? Yes, still remember these equations? These are what you use for ideal gases. Then which one of the following correctly represents the deviation of a real gas from an ideal gas? So gases. Right. So basically, long and short of it is that's how we will function this year. We will look at a topic. We will extract questions that have to do with that topic. We will work through, let's say, hopefully 5 questions per tutorial so that we can have some fun. Right, so this summarizes what we have for today. If there are any questions, feel free to drop them on the WhatsApp chat group. I see that we also have some activity on that group. So if you are available to send the questions, you can just label them as chemistry questions. That way it will be at least easier for me to identify amongst the many messages on that group. Okay, so this summarizes our work for today. That's our chemistry work. We have planned and we now know what we will do throughout this year. And the task is already there. You already have some homework. I already gave you some homework. So there are some questions that you are expected to attempt. I think we're done for today. All the best. Let's meet next week, molecular structure, so that we can go into the next topic in the next month and so forth. All the best then. Have a fantastic day and a pleasant weekend. Nyasha here. Enjoy yourselves. Thank you.